Okay, so I didn't want to write it down because if I write it down, but I can give it on an example. Writing it down makes it more confused for most people. So suppose, let's say that you have, I guess, right, and here, of course, my problem is that the betas, of course, are not the same. I mean, the betas are kind of almost the same because it's either log or constant function, but after partition of unity, they would not be quite the same. And here the alphas, again, they are the same here, but after partition of unity, they might not be. But suppose you have something like sum over n1, n2, n1, n2, and 3 of alpha 1, alpha 2, alpha 3 with n1, n2, and 3, n1, n2, beta m1, beta m2, beta m3, and suppose you want to do, let's say, n1 with m2 and the remainder m2, m1, m3. So this would be the sum of alpha tilde. This would be m, this would be n. Alpha tilde m, beta tilde n, and whatever other coefficients, and let's say alpha tilde m would be the sum, because here you have some k of the product. Well, would be the sum over n1, n2 with m of n1 is alpha 1, n2 is beta 2, I guess. M2 and beta tilde you can measure. That would be. Any other questions? And it's x delta 1. The positive delta 1, but the small delta we don't care about as long as you focus. Small delta 1 is even if you do the small delta that works, it's fine. And now we can in fact absolute value. And we want to gain x over log x to the n. These two sessions of today for me, so I'll be one this morning and one this afternoon.
So I'll just first do a few more words on the topic of last time about the divisor function in arithmetic progression, and then today I will mostly talk about the original Zhang approach to bounded gaps between primes and try to motivate some of the steps in his method and bring out some of the key points and key difficulties in this work. And then this will lead to exponential sums of finite fields somewhat similar to the Kloosterman sums we saw yesterday. And in the last two lectures, tomorrow and Friday, I will explain some of the main ideas and results for exponential sums of finite fields. So let me start then, like this quick reminder, so this will be quite fast. So yesterday we had something like, so we wanted to study the divisor function in arithmetic progression, so we had some smooth weights, V1 and V2, which we think that V1 is like the characteristic function of an interval of length m and V2 of length n, and there was this application of the Poisson summation formula which gives an expression which is really close, at least in spirit, to a sum now with new variables h1 and h2, where the lengths have been symmetrized compared to the lengths of the original ones, and to get something that's exactly correct. Let me copy exactly what I had. So then we have Kloosterman sums, where so SABC is the Kloosterman sum defined as the sum over x invertible modulo C of E of AX plus B times the inverse of x modulo C. Okay, and there is this theorem of André-Weil that tells you that, roughly speaking, you almost always have square root cancellation in the Kloosterman sum. So if basically A, B, C are one co-prime, then modulus S, A, B, C is less than the divisor function of C times C to the 1/2. So for any positive epsilon, it's of size C to the 1/2 plus epsilon at most. And the point is that if you want to apply this, there will be some degenerate cases that you have to handle. So the way this is done usually is to just see what happens when you don't have square root cancellation and hope that you get something that can be evaluated explicitly that you then combine in the main term. If that doesn't work, then you can always try to check that this, you can try and guess what the main term will arise from and check that if you take, let's say, q equals 1, then this will lead you to the same expression with a factor 1 over phi of q to make the cancellation work out nicely. And this is indeed something that happens in most applications. And this is because the main term in the most simple-minded heuristics to guess asymptotic of the divisor function in arithmetic progression, the main term is the right one. It's not like the prime number theorem where the main term is wrong if you just use inclusion-exclusion. So for instance, so the simplest case is when C is a prime, then it's very clear what happens. There are two cases that you have to think about. And let's say that we view A and B as defined modulo C, which is a prime. So SA is BP, 0 BP. If B does not divide, P does not divide B, well, you can see what happens. Then the A is 0, so you have X bar runs over all invertible classes again by just replacing X by X bar. So this is a Ramanujan sum. So it's -1. And if both A and B are 0, then this is the only case where the sum is large, and it's, in that case, P-1, which would be phi of C in the general case. So from this, if you suddenly take the case Q equals a prime in this divisor function in arithmetic progression question, it's quite easy to see that the main term will only arise from A and B. So that means H1 and H2A both divisible by Q. Because of the range of the variables, that means essentially that only H1 equals H2 equals 0 will contribute. Okay, because you have the sums are going to be too short to have contributions from other multiples of Q, and you're going to get P minus 1 coming out from there, and from this you can detect the main term. So that can be kind of an exercise. I'll leave this third board for later. So exercise then. So check main term. At least when Q is infinite. So when Q starts not being a prime, you usually have to do a little bit of additive or multiplicative sum elementary combinatorics to get exactly the right thing. Because you could have common factors of various sizes, so this usually involves some identities between multiplicative functions. But they are usually not too hard. And again, if this turns out not to work, in many cases by just reversing the process with Q equals 1 and checking to see what is the main term that comes out there that you can maybe compute independently anyway, you can check that it cancels out. Okay. So I'll come back to Kloosterman sounds later. So just a few words now. So examples of a very general class of exponential sums for which we can prove this type of squared cancellation because they are related to algebraic geometry over finite fields. Okay, and so tomorrow and Friday I will explain some of the steps that are available, some of the techniques that are available to handle these things. So one typically emphasize finite fields despite the fact that C is really a nice field. It's because using the Chinese remainders theorem and other types of techniques, it's most often the case that the critical situation is when the modulus is a prime. Okay, so in the case of Kloosterman sum, this is, for instance, what Kloosterman did in the 1920s. He introduced these sums for the purpose of studying the number of representation of integers by diagonal quadratic forms in 4 variables, positive definite, and he proved the first non-trivial bounds, which were not as sharp as that, but were sufficient for his purpose. Okay, I'll give some reminders of this historically. Okay, so let's go then to the third section. So it's really now about primes in arithmetic progressions. So it's quite possible that some of the things I'm going to say today will be relatively technical. Actually, they will be relatively technical. It's just the fact that the type of techniques that's involved in Zhang's proof are quite delicate and complicated. So in comparison to almost everything else that you've seen in this lecture since the beginning of the school, there are steps which are very hard to motivate in a reasonable amount of time. So there are some steps I will tell you, okay, we do it this way, and I don't really know myself how you would motivate this deeply. I think there's a certain amount of trial and error that went into this work, starting from Fouvrier and Ivanets in the 80s. Okay, so let me remind you of the motivation. So the goal now is to say something non-trivial and unconditional about so the exponent of distribution for primes. So let's say for the von Mangol's function, which is almost the same thing for moduli which go beyond the Bombieri-Vinogradov theorem. So, because we want something unconditional, there's no hope of trying to get a strong exponent of distribution, because that would tell you something about the Riemann hypothesis that we don't know today. So we try to necessarily do the same type of averages as in Bombieri-Vinogradov, and in fact one has to restrict these averages in various ways, because there's no known really complete analog of Bombieri-Vinogradov beyond square root of x. So let me give two motivations quickly for this. Actually, I guess I can give three. So one is curiosity. There's a natural boundary which is square root of x that arises from Bombieri-Vinogradov, which is actually a natural boundary for exponents of distribution for a very, very large class of arithmetic functions. So it's natural to try and see if we could go beyond that.